We got the big one today. We've got the molecular shape of you. Amira says this is the first of your songs I heard and probably still my favorite. I mean, so Amira, you're definitely not alone. This was the song that kind of launched the current phase of my career, I guess. Um, I was lucky enough to 2017 was a good year to me, I think. And one of the reasons it was a good year to me was just that. Oh, do you guys want to get some water? Yeah, I could use some water actually. Let's just a quiet little water break. Hmm. Yeah, I mean, statistically speaking, probably about half of you discovered me from this video, given just the numbers, because like when I started, by the time I had done Bohemian Gravity, I had 40,000 subscribers, and then after that, I uh, I went very slowly up from 40 to like 65 for like from there until here. I was at something like 65,000 subscribers, and then after this video, I went up to like 150. I think I might have passed 200,000 on this video. And then when Evo Devo was also a great success, that like bumped me up to close to where I am now. So of all the people who stuck around, it is two of probably about half of you. It's because of this video. So um, yeah, show of hands if you want who discovered me through this video. So this started as a very, I don't know. It was actually like uh I don't know. For a long time, I didn't think this video was going to be very good because it took me a very long time to get the lyrics together. Like, the idea was, okay, like, it didn't start trying to be like building up life from like the beginning of physics. It started with me wanting to explain basic chemistry. And I was like, okay, there's this song called The Shape of You. I listened to it. I think I first heard it on like an Adam Neely video, which shows you how much I pay attention to the actual radio. That I had to hear about it from like music theory YouTube. But I heard the Shape of You, and I was like, okay, this is actually a good song. Seems to be a really popular song. I would be willing to take this one on, and it's got shapes. And the obvious thing to do with it is like shapes of molecules. And I think I came across at some point like a really random article that reminded me that like molecular orbital theory existed, like that which is something that I feel like is just a little higher than you get in like a basic science survey, like I don't know, year one science before you pick your major or whatever. You learn about orbitals and you learn they bond, but like and then if you go further in chemistry, you learn about aromatic bonding, and they just kind of throw it in like, oh yeah, now they're like, we're gonna replace these double bonds and single bonds with like these resonance structures, and you're like, what's a resonance structure, and how does that work into like my previous understanding that there's like fixed orbitals that stick together. And I was like, okay, that's a cool little insight about, how the electrons are actually like delocalized around a whole section of the molecule that I could tackle. And it's got something to do with shapes, and this is about shape of you. So I'm gonna like start putting this together and see what happens. And I got stuck 2/3 of the way through. So I was like, okay, I'm gonna start with physics, and like because my background is theoretical physics, I was like, well, you gotta start at the bottom. You gotta start with the Dirac equation and everything. And okay, so I know what I'm gonna do for the first verse. I'm gonna build it up like to the point where things are bonding. I know what I'm gonna do in the second verse. I can expand into different types of bonding and into um yeah, and like I didn't have a thing for the ending and like the last chorus. How to like, because okay, so here's the thing. I use this video a lot as an example in my lecture about storytelling, because Ed Sheeran is really good at crafting like a narrative with his words and matching it to the emotional flow of the song. So a pop song will often have something like a story structure. Like if you've ever taken a literature class and you've seen these like graphs of story structure where it's like, like rising action, and then second rising action, and then like big climax, and then denouement, whatever, and like slows down and ends. That's like a very standard story structure that for some reason is very emotionally resonant to people. So people keep doing it. And it's also an emotional structure that resonates in pop music, and pretty much all pop music follows the same format, right? Like there's some action, there's like a chorus, which is like a local peak, like a local climax, and then there's like a second verse that dips down and a second peak with a second climax, and then you like build up to a grand finale thing and end. And it's nice if you're doing a song parody, or if you're just writing a song. Best practice is to take whatever emotional structure that your music is fulfilling and match the lyrical content, like the story that you're putting into it. You want to match it onto that, right? You want to get it so people are feeling the story through the words, right? And so Shape of You has this great build up at the near the end. Come on, be my baby. Come on, be my baby. Come on. And I couldn't think, I had this, like, come bond with me, baby, come bond. Like, that was one of the first lines I wrote that made me go, okay, well, that's an easy fill in. Like, when you're constructing parodies, the other thing that I do a lot is that I'll look at kind of the key lines. Like, what are the hooks? What are the things that, like, if you've heard the song twice, here's what you definitely remember, because those are the ones you really want to stick in a parody and like nail to the wall. Like, this is something that really works. And if you get those, then there's a lot of play in the joints with a lot of the rest of the lyrics. You get them as close to the original as possible, but it doesn't really matter if you get them precisely on, because you've hit all the points that are really central in people's minds. But this song has such a spectacular conclusion that I didn't like. I was like, well, I could take it into like salts and like ionic bonding and crystal structures, but that's just not great. And so I just didn't do it. I like recorded the whole song. And I recorded the first two verses, and I thought to myself, okay, I've got a lot of animation to do. This is very much in the style of Ed Sheeran's lyric video. I took very closely like the color scheme and everything from it. So I was like, okay, I know what I'm doing for animation, at least for the start. I'm just gonna go with it. I'm gonna do 2 verses, and then like by the time I've done that, I'll have spent so much time with this song that it'll probably like be in me. And it'll feel really natural. Maybe it'll feel really natural of where to go next. And by the time I got there, I was right, because where it felt really natural was to just... Oh, the other thing was at some point I thought Molecules Take the Shape of You would be a great final thing, as like bring this all to, to a big head of like everything's made of molecules, and that's in fact what everything is. That's like a really satisfying conclusion, right? And with that, the obvious way to go was into microbiology, right? And like molecular biology and microbiology, and string you together out of atoms and molecules. And then like that's when, as soon as I realized that, I thought this is going to be a good video. because you can have a good video that is pretty good all the way, and you can have a video that has one really good message and like sticks the landing, but is mediocre all the way. But this was a video that I was really satisfied up to this point, and somehow I stuck the landing in terms of figuring out where it was supposed to go in the end. So yeah, like releasing this, I had a sense that people would like it, like compared to what I had been doing before. I was like, this one will probably take off pretty well. I did not expect the influx of people that it actually achieved. But it was a very pleasant surprise. Yeah. Anyways, let's give it a watch, and I can comment it as we go. So the cartoonish. This is very similar because Ed Sheeran has like a divide sign and a plus sign and stuff in his starting thing. This is supposed to be a very cartoonish. There's like a bunch of layers, like levels of drawing complexity in this that simplify and simplify and simplify. But here's your p orbital. P orbitals are actually much broader than this. They're more like a circle with a line cut through it than like a thing like this, like you would see in a lot of chemistry classes. But s orbital, p orbital, these are 2 different ways that an electron can orbit an atom. We'll see a lot more of that. Hey, we've got you can see as it flashes to different. What am I doing over here? As it flashes to different ones, this is like a frame perfect thing you would have to see. But as it flashes, I've done like the resonance thing where this becomes a double bond and this one like disappears for a frame. So sort of like momentary localization of electrons. This is just, I don't know what this molecule is. CO3. It must be an ion, right?
A dot isn't the best way to try to sum up how electrons come and go. They are the states of a matter field that follows an equation the Dirac wrote.
Okay, so this is the part that if you're a chemist is probably like because this video goes through a few different levels of science. Like it's my understanding of physics and then my understanding of chemistry and then my understanding of like biology. Like this is if you're a chemist and you haven't gone into physics, then this is probably the part that's new to you. So this is the Dirac equation. This is the replacement. It's sort of you can think of it as the relativistic version of the Schrodinger equation. So it's more than that. It's really a field equation. So I've talked about this a lot before, but the matter in the universe is made of fields, quantum fields, which are you can think of them like, I don't know, like air or something, like as if there was some sort of medium all through the universe. Like back when if you've ever heard the story about how they disproved the ether, Michelson and Morley disproved the ether because people used to think that waves need something to wave through, and they thought that light waves waved through this thing called an ether, which would be like a medium, like it would spring up and down and transmit waves. It turns out that there are things like ethers. They just don't behave the way Michelson and Morley expected them to. And like that was what Maxwell wrote down in his field equations for the electromagnetic field. But there are other fields. So everyone kind of knows about fields. They know about force fields. They know about the electromagnetic field, which is like magnetism and electricity. And light is a wave on the electromagnetic field. What people almost never know unless they have been in a few physics classes and possibly gone to grad school in physics, is that matter is also a vibration on a field, exactly the same way that light is. It's just a different sort of field called the Dirac field, and this is similarly to the way that Maxwell's equations describe the classical electromagnetic field. This describes the classical Dirac field, which means it's just the field equation before you apply quantum mechanics to it. But it turns out that you do have to apply quantum mechanics to it, and that makes quantum mechanics turns field equations that just result in ripples into particles. So your ripples are still ripples, but they become quantized. So you can have a ripple of a certain size, or a ripple of double that size, or a ripple of triple that size, and that corresponds to 1 or 2 or 3 particles. And you can't have anything in the middle of that. So that's where we get this notion of particles. The big difference between Dirac fields that make up matter and force field, like you call them bosonic fields, but like force fields essentially, things like electromagnetism or gravity, is that photons can pass right through each other, and they can also like add up. So like a bunch of photons can add up into a big wave, which is what you see if you've seen like anything with like laser diffraction or anything. It's a whole bunch of photons all adding up together in the same state, forming this big wave that then makes visible the wave properties of light, which is why it was so easy to figure out that light is a wave, because it diffracts like a wave and does all sorts of things. But the thing with these ones is that they can't add up. Once you get one of them in a certain state, like in a laser, all the photons are basically in the same state. They're all adding up. But with Dirac field particle, once you've got it vibrating in one state, you can only have one size of vibration. You can have a 0 or 1. You can't have 2. 2 doesn't exist. If you want another particle, another little packet of energy, you need to choose a different way for the field to vibrate. And so when people talk about, like you know about that from chemistry. You know that like you can fill up the first shell of an atom with 2 electrons, and then you have to go out to the next shell and fill it up with 8 electrons and whatever else. And if you've gone further into like orbitals in chemistry, you'll know that corresponds to, like, the first one is s orbitals, and it's the reason why there's 2 in the first orbital is because you can have a spin up one and a spin down one, which correspond to different ways that the field vibrates. So the field can vibrate in an uppy way or a downy way in this certain spatial configuration, and then it's done. Then you've maxed out. Usually in chemistry, they just call it a quantum phenomenon and whatever. And it's kind of, so Alex is asking, what keeps fermion fields from doing that? It's like they literally can't, right? There's no way for them to, so you can imagine it's a bit like a bit flip. So like if you have a computer with a whole bunch of bits on its memory, it can either have the bit be 0 or 1. There is no 2, right? It's just not part of the structure of the disk. If you wanted something that went 0, 1, or 2, you wouldn't be using a binary system. So fermion fields are essentially like they're made out of binary system type 0 or 1 resonators like that. And there just is no 2. So once you get 1, the only thing that you could do would be go back to 0. And there's like various mathematical ways of like capturing that phenomenon, but really that's all that's going on. It's just like it's a system that only goes 0, 1, and that's it. So in the end, you have these vibrations pile up on each other, right? If the one's taking up a certain spatial configuration and another one's attracted to the same point, it can't get there. It's blocked by the fact that there's no more space within the parameters of the field for it to get there. So it has to add up on top of it and add up, and that's how you get these shells. And that's why matter feels like matter, because it's hard. It repels itself if it gets too close. So that's all contained within the Dirac equation fundamentally. And if you do it in chemistry, you really only see it as it's a given. It's like electrons work this way. They work by the Schrodinger equation, which is what happens when you take the Dirac equation and you do it in the limit of like really low energy. So you're not worried about the speed of light and stuff. You're kind of taking out the parts that matter when the energy is really, really low. You get the Schrodinger equation, and then it's just also a given that electrons can't all be in one state, and you don't really know why. It all comes from quantum field theory. That's a lot of a rant on one thing, but like that's pretty much the entirety of the physics part is this next like 3 seconds, and then we move on to chemistry. So I feel a little justified. Let's continue.
The Schrodinger part of the whole equation will just lead in subs.
So there's just a very brief animation of us expanding out. This is called a Taylor expansion. This is this would be a Taylor expansion. So I don't know if you've seen Taylor expansions. This is just writing out. This is kind of the reduced, simplified form of the equation. This is the complicated form of the equation. Here's if you take the non-relativistic limit, which is kind of corresponds to these things, then what you end up with is this, which is the Schrodinger equation, plus additional terms which are they're of the order your velocity squared over the speed of light squared. So the smaller your velocity is compared to the speed of light, the less the rest of this junk matters. Like this expands out to Schrodinger equation plus a whole lot of junk. And if your velocity is close to the speed of light, then you have to worry about that junk because this is going to be about the same size as this. But if your velocity is really low, then the square of your velocity is going to be even lower compared to the square of the speed of light. And you can safely ignore all this and you reduce down to this nice thing, which is the Schrodinger equation, which is what chemists always use because electrons are not really going too fast. But you do have to start worrying about that as you get farther down the periodic table. That's why you start to see wonky things going on with like heavy elements breaking some rules of chemistry. Like one of the reasons that gold is golden. I think the reason that gold is golden has something to do with the electron. There being so many electrons that the ones whipping around the outside are going like an appreciable fraction of the speed of light. And so this would not necessarily apply in that case. But it works really well for like the first 20 or so elements.
Equation will just lead in sub C when it expands. Now get that Coulomb and add it in with the proton.
Oh, so this is the this is the free Schrodinger equation. This is what happens if your electron is just going through space, nothing going on. But if you want anything interesting to happen, this is the Coulomb term. So Coulomb forces are electromagnetic, or like the simplified version of electromagnetic forces. This is hiding the fact that actually the electromagnetic fields are quantum and they're they're exchanging virtual photons, which is what happens when you quantize the electromagnetic field and all that. But for chemistry, you don't worry about that. It's nice, your nice old Coulomb potential. You probably many of you have seen this. You got to add that into the Schrodinger equation, and that's what gives you these nice. You got a point source, so you get nice spherically symmetric solutions out of the spherical harmonics.
Get it in with the proton and watch them start to dance. It's hydrogen, it's like, oh,
Quick field lines
proton,
there.
I feel your tug, central potential, dip down, pulling on me.
So we can also there's two ways of seeing physics generally with Coulomb potentials. You can see it as a force pulling in the object, or you can see it as a potential. So that would be your particle can gain it will gain energy compared to what it was out here if it slides in here, because this potential field has like negative potential. So there's sort of potential. You can think of it as potential energy stored up between this electron and this proton. It's kind of it's a weird sort of fiction thing to think about, right? That like, oh, all of the electrons and all of the protons in the universe have all this massive amount of potential energy stored up between them that will get released if they happen to get close to each other. But it's energy conventions are kind of arbitrary, and it's one way for them to make the math work out. And it lets you draw these nice graphs where here's the advantage of the potential of the potential frame of reference is that you can get rid of this electron and still show what's going on with the proton. The proton has a potential. This is like from the perspective of the electron, where the proton's doing all the work. It has a potential and the electron's falling into it. Whereas actually a proton has a potential, but you could just as easily think of the electron as having a potential and the proton pulling on that potential well and causing it to drag over here. It's just different ways of looking at the system.
But I'm not falling in deep. No, that would break uncertain.
Aha, I got this wrong. This is inverted. So this is the uncertainty principle. Delta X, delta P is less than h bar over 2. That's a thing that can't happen. So actually, the proper, lots of people pointed this out in the comments, but the proper one has the greater than the other way. Let's go back to that. Where are we? Yeah, this. This should be a greater than. This is also quantum mechanics. This is the famous uncertainty principle that people always call it errors, but it's really like you can think of it as the spread of this electron, because the electron is a wave. A wave has some sort of spread in space, right? It takes up space, takes up a certain amount of space, but there's another way of seeing a wave which is in like momentum space or frequency space. So for example, a wave that's just like this all the way throughout the universe. It's just steady. It never changes. It's spread out everywhere. That wave has no localization in position space. It's everywhere at the same time, but it has essentially infinite localization in frequency space. It has one frequency all across its spectrum. If you Fourier transformed it, it would be a single point in the Fourier spectrum. Whereas there are other waves that are like a wave that's everywhere in frequency space. So it like is a combination. Waves are combinations of modes, right, and of like different frequencies. So you've seen like a frequency spectrum for your equalizer for your sound or whatever. Any wave you can imagine can be broken down into different frequencies. A wave that's a combination of all possible frequencies can be localized in space, and a wave that's a combination of all possible space positions can be localized in frequency, but only one of those can happen at a time. If you have some spread in frequency space, you have an inverted amount of spread in physical space. And so this isn't really a quantum mechanical phenomenon, this fact that the spread in position and the spread in here it's momentum, but momentum in quantum mechanics is the same as the frequency of your wave, up to like some factor that gets the units right. This is just a general statement about waves that you can't have. They can't be both localized in position and in frequency. It doesn't make sense. It just falls under the definition of what a wave is. So the only thing that's really quantum mechanical about this is setting like what the scale of this frequency position relation is, and the scale of it is this Planck's constant h bar. So an electron can't be more localized in position and in frequency at the same time than this h bar over 2. And that's what causes the electron in this case to not collapse into a point around in the middle of this proton, because if it were localized inside that proton, it would be so spread out in terms of frequency or momentum that it would shoot out of it in a bunch of different directions. And if it were really local, if it had almost no momentum, then it would collapse inward because it would have no momentum with which to escape. So this is what it ends up having. Even if there's no like rotation of it going around the proton in any ways, it comes down into this stable configuration where there's a certain spread in the position and a certain spread in the momentum that keeps that spread in position from collapsing. And that's just how it is. That's how you get your orbitals. Yay! No, I won't break uncertainty.
Uncertainty, say, oh, electrons move too much. Slow down your pace and put that.
That's there was a guy who did a professor who did like an explanation of this video, and I was really happy that he caught this thing that happens right here, because you'll notice that the electron comes in. If an electron is coming in to a proton, if it has enough energy to have been out here, then it's going to do the same thing. It's going to do like a close pass and then like a whoosh and leave again, right? If you want it to stick around the proton, it needs to lose that potential energy somehow that it's falling in with. And usually what happens is that it happens to emit a photon at the right time, and then it gets trapped around here because that photon takes away the extra energy, and you don't, now that your electron doesn't have enough energy to escape again. So I put a little photon streaming away, and I'm glad they caught that. See, there it goes. So that's this is an excited state. Usually when electrons get captured by a proton, they'll be in some sort of excited state. They won't immediately be the lowest possible energy state. The reason why they generally, like, there's often in chemistry, there's this idea that electrons want to be in lower energy states. You should always be wary when you hear someone say that an inanimate object wants something. But what's really going on is that if your electron is in an excited state, there's something that can happen that will knock it down, which is that something will jostle it and cause it to spit out a photon, and then it'll get knocked down to a lower energy state. Once it's there, unless some photon of the exact right energy comes in and hits it, it doesn't have the energy to jump back up to an excited state. So like an orbital that was like this alone, like imagine that there was one atom in the entire universe and it had one proton and an electron like this around it in this state. It wouldn't change. It wouldn't want to go down to its low energy state. It would just stay there forever. Actually, that might not be true. There might still be a possibility of, it depends what state you started with. There could be a possibility of it emitting a photon, but you'd have to start it in kind of an unstable state anyways that had some probability of that. But it's mostly that in the real world, there's thousands of atoms and they're always jostling each other and messing with their and they're messing with their orbitals in particular ways. And so something's going to happen that causes this thing to emit a photon, and once the photon is emitted, there's no way to get it back. So then it stays down there. Come on now, follow my lead. So there's that photon going away. Fun dance of exchanging photons. That isn't really realistic, but I like it. Yeah, okay. So there's better ways to talk about this. This is pretty self-explanatory, I think. I don't know if it's self-explanatory. I mean, we've got the upspin and downspin. If you wanna know, like, in terms of physics, what spin up and spin down means, the answers to, as far as I can tell, the answer is that no one in the world has an intuitive explanation for it. So this is one of those places where, like, we kind of bump up against the limits of what people have figured out how to do nice and pedagogically. Like I've been doing this quantum field theory video, and I've been looking for like an intuitive explanation of electron spin for a year now, and I haven't found it. So if anyone knows if anyone knows how to do that, what, like Alice is asking, do spins really mean anything? Yeah, they do. They mean they give the electron a particular magnetic moment that causes it to affect electron to interact with magnets in particular ways, and like they have there's a definite difference between a spin up and a spin down that corresponds to the way that the quantum field is waving. So there's some way that the quantum field is waving in a counterclockwise way versus a clockwise way, but like making that comprehensible to the lay person without just without doing it out of the Schrodinger equation or the Dirac equation, I haven't figured out a way. So anyways, it is just the raw fact that electrons come in two types, spin up and spin down. And now that you've got these two together, there are two possibilities kind of for how these orbitals could combine. They could combine in a way that sort of adds probability to them being in the middle, which is nice because then they're close to two different protons. Or they could combine in a way that where both of them are kind of avoiding each other here on the side. And they don't take that one, obviously, because that one's way more energetically costly. If they started in this one, once again, it would be like the P to S transition. They could just collapse down to that. So that's the steady state. There's H2. Wee.
Hydrogen as a rule is found in nature as H2 energy configuring a molecule.
It's that same thing, but we're mapping out the energy. This should really have this. I'm not entirely happy with this diagram because it, as a physical process, it doesn't make sense that the energy can't just go down. This thing would have to be emitting photons or getting jostled by other stuff to make it work. Okay, I didn't do it. I thought I might do the thing where I show the anti-orbitals. I do it in the aromatic bonding where I show the orbitals that are actually filled and then the anti versions of those orbitals that don't get filled that have more energy. So we'll talk about that then. Not anti-orbitals, but like the orbitals that are like, because when you combine these two orbitals, you like add them up and you figure out what, like, now so far there's one state that this can be in and one state that this can be in. And once they combine, anti-bonding orbitals, that's what I mean. Once they combine, there's one state that they'll both be in and another state that neither of them are in. And the other state would be one where instead of them being super close, they would both be like avoiding each other out here. Like it's kind of like you take this and you subtract off the individuals from it and see what's left. That would be like the other possibility for them. Like if you wanted to get two more electrons around this pair of protons, this state is now filled up. And the only state that would be left would be to take like these weird sort of earlobe sections out here, which generally doesn't get done. But that'll happen in like ion things. Can you have, is there an H2 plus ion or H2 minus ion? Is that even a possibility? I don't know. I like that spin. I was getting a lot better at After Effects at this point. Like figuring out how to do like spins and motion blurs, and all of these like this like wibbly wobbly stuff. This is just hand like mouse drawn in After Effects. I kind of went like I just kind of scribbled around for one frame and then for a next frame and then a next frame and then a next frame, and once I had a loop of 5 or 6 frames, then I just looped it. So all of these orbitals come from things like that where I've just like. Actually, I think they might all be the same, because this was the first one I drew. It was kind of the squash, this circular thing. So I took that little I took this little thing, and then for the other orbitals I like squished in various ways. So I think for the bonding orbital I just like stretched it out a little bit in the X direction. For these ones I think I drew new ones, but I did some scribbles in rough lobe shapes for a few frames and then looped them again. Yeah.
Atomically bonding. Low, high, low, high, low, high. Atomically bonding. Energy configuring a molecule. When
All right.
take the shape they do.
One done.
On a twin, one up, one down in the ground state.
So there's the spins again. This is if you don't recognize this, this is quantum mechanics notation. This is just how you. It's not really important. It's just how you notate these states in quantum mechanics. There's this thing. This is called a ket. The reason why it's called a ket is that if you want to get a number out of it, you have to multiply it by a one that's the opposite side that they call a bra, and so you get a bracket. So it's just a bad physicist pun. The reason why these are called ket vectors, they are vectors. These are like in quantum mechanics, every state, which is like some way that the field is wobbling, is it because there's a C in the, like they put the C in the middle? Why is there a C in the middle for bra and ket? I'm not sure. But thanks, Alice. That's kind of helpful. Jamil says H- ions are possible but rare. Yeah, I figure they would be, because even like with all of the bonding orbitals filled up, you'd think that there was more, like there was less than zero potential energy to be, or more than zero energy to be gained by another electron coming in and buzzing around the side of two protons. Because the electrons are all in the middle and the protons would be closer. But anyways, not very likely, because by that point you've got a neutral atom and you're just kind of working with local effects. I don't know. So yeah, anyways, this is just how this is saying that if this particular spin, this particular state, if you hit it with this spin operator in quantum mechanics, which basically just tells you how much spin the thing has. But spin, what does spin mean? I don't know. Anyways, what's important is that up you have angular momentum of h bar over 2. Down you have an angular momentum of anti-h bar over 2. This is a real angular momentum. This is why like spin is definitely a real thing, because these are real angular momentum values. Just what do they mean? Like, and how does, my question is where's the circle? You know that thing that that 3 Blue 1 Brown always asks when he's doing pi videos, where's the circle? This is my question about quantum field theory right now. There's a circle that's causing angular momentum somewhere deep in the theory, and I can't find it right now.
On a twin, one up, one down in the ground state with S&P.
That's how I chose to do neutrons with that neutral sign. That's cool. Okay, here's the p orbitals, first excited states. This is, so you can think of these as the electron actually has a little more momentum now, or at least a little more spread in electron, spread in momentum. So like this first one, minimal spread in momentum possible, minimal energy, but if you have a wave with a little higher frequency, you can have a little more energy in it. So for this one, you can think of it as like vibrating in this direction, like sort of sandwiching back and forth, and bouncing off each other, or like going through itself like this. You can think of the 2p as that, and then the p is just another thing. But this, I was trying to do it in the z direction, but it doesn't really come through here. It's okay. It's on the screen for like 2 seconds. The interesting one is the 2s, because that's the one where there's kind of like a more of a radial spread in momentum. So your electrons, like if your electron was a point particle, you could think of it as like going through the center and out the other side and then coming back like this, but it keeps interacting with itself in a way that makes it's like a centrally going out wave instead of a wave in a particular direction. There's also ways of seeing these 2px, 2py, and 2pzs that are more like orbiting. So you can combine, if you combine these in particular ways, you'll actually get orbitals that, instead of having a nice node like this where it's kind of like sandwiching in on itself, you combine 2px and 2py, for example, you get something that kind of like, you can't represent it. Here right now I'm representing this as like a positive value and this is a negative value. And the reason why they always do orbitals in this way is that this is how they end up working for bonding purposes in chemistry. But from a physical standpoint, if you wanted to make the connection between like an electron going around a nucleus and like a planet going around a star, there's an alternate way of seeing these where your wave goes around in a circle. You add one of these and one of these, and you get your wave kind of waving around in a circle like this. And there's no particular node, but it's got like an angular, rotating angular momentum to it. And the more, like the higher energies you get, the more you can really localize that as like going around in a circle. And so if you get high enough energies and high enough masses on or rotating things, there's kind of this smooth transition from looking like this to looking like just an object orbiting around another object, which is what we see in like the macro scale world. So it's nice to make that connection because sometimes you kind of miss it. Like how on earth would you get from this at the small scale to like a ball going around another ball in the large scale? There is actually a way to get from this picture to that picture. So that's nice.
In quadruple degeneracy, the second shell can be filled up with 8.
So these all, I don't think these all have technically the same energy. This one's like am I right? Yeah, this one's a little less energy, but they're really close to each other. They all have the same quantum. They all have the same total addition to their momentum up to tiny little corrections.
Quadruple degeneracy, the second shell can be filled up with 8.
So they're kind of all equal for the purposes of chemistry.
The higher angular power spread all the beautiful flowers in middle.
Oh, and there's some fine ones. So then like once this is the simplest possible waves you could have.
The second shell can be filled up with 8. The higher angular.
But there's just like a whole bunch of ways that you could get a wave that is like, these are all basically solutions to what if you had a wave that was attracted to a single point? What could it possibly look like? And one of the ways it could look like is something like this. This is actually like, this is kind of close to what I was talking about with starting to get like a wave going around in this direction. What this would actually correspond to is kind of like a superposition of an electron going this way at a pretty high momentum. So it has a few wave turns before it gets around, but it's interacting with a superposition of itself going around the other way. That didn't make any sense if you're not already a physicist, but basically the rule of thumb in these sorts of things is the more nodes you see, the higher the energy. The more these points where the wave is canceling itself out, or the more cycles you see, the more it's repeating before it goes around, the more energy you have in your system. And it makes really cool pictures. I think this one's supposed to be tetrahedral, but it's not easy to show that. Like octahedral, and then that's like I don't know, that's weird. Anyways, these are cool. These show up in transition metals and such things. Yeah, these ones. Someone told me that I got this wrong. I did it because if you want to do bonding, you're going to have to put one in each state to get it to bond to 4 things. But when you start out with carbon, you actually would fill up the s orbital first and just have 2 of these going on in the default state, and then once it gets attracted, once it sees the bonding hydrogens, they'll jump to these states. But I don't want to do that; it's a little too complicated. Okay, so at this point, this is like I'm animating. I'm like, look, this is getting. I've sort of reached the limit of what I can do. Like you can imagine that every one of these takes like half a day of work to put together. So I'm like working within this framework, and I didn't know where I was going to get to at the end of this animation when I started. So I start off here, and I'm working in this framework of, okay, my electron is kind of this jumbly thing, and it's around a proton. And then at some point I get to this, and it's like, well, that's kind of the limit of what I can do with this particular framework, because it's just a blob with a bunch of arrows. Okay. Well, what are we going to do? Let's simplify it down. We're going to go back to like the more standard. Now that you understand what orbitals actually look like, let's go down to like sort of the cartoon version that you see in your chemistry class, and we'll work with that, because there's a reason why people use simplifications in cartoons. It's not, it's not accidental. It's not that they don't know the reality. Well, I mean, some of them don't once you start using the cartoon, but people know what's actually going on. It's just like to accentuate certain things. Sometimes you want a cartoon, so let's make a cartoon.
This ain't nothing tricksy, but we're gonna make some
This is your
method
cartoon
today.
model.
With
It's still pretty
hydrogen
complicated, right?
inside. Oh, atoms, I feel your
So here's your new hydrogen. A lot simpler than that big bundle of field stuff.
tug. Got my electrons plugged out, pulling on me. Come on now, settle around me. I'll hybridize to sp3.
Okay, hybridization. This is a thing that when I took chemistry was really confusing to me because no one had taught me quantum mechanics, right? And it's really weird to like you learn about these orbitals. It's like, okay, there's like an s orbital. This is the way that the electron can be. There's like other s orbitals. There's p orbitals, whatever. Okay, like the electron can orbit around in these sort of lobe things or whatever. And then all of a sudden they tell you with hybridization, they're like, okay, this is what happens when like now these orbitals can be mashed together. And that doesn't really make a lot of sense if you haven't actually done quantum mechanics, because it's just totally out of the blue, right? At least that's how it felt to me. Nathan is saying I answered the daily discussion today, and the stream is going to be 2+ hours. I definitely have some good luck. Yeah, I'm sorry. I think we had too much fun at the beginning of this. This is gonna stretch out. I'm sorry, but I'm also gonna keep going and get to the end of this if it kills me. So hybridization. So the thing that I was telling you before, all of these conventions are arbitrary. So what's going on in quantum mechanics is that the number of states you have are represented as vectors in a vector space. So if you've seen a vector space, this kind of vector space is actual like 3-dimensional space. And a vector in the vector space is just a direction and a length pointing in some way, right? So there are 3 dimensions in your space. So you can make any direction in space by adding up some length of vector going this, some length of arrow going this way, some length of arrow going this way, and some length of arrow going this way. If you add those up, like with the points on the other one's tails, you can get to any point in the space, right? So there's this notion of a basis, like what's the minimum number of vectors that you can use to add up together in all the different possible directions and get to any point in the space. And in this case, a point in the space represents some sort of way that the field could be wobbling in. We map all these different ways that the field could be wobbling into points in a space with some amount of dimensions. In this case, if you're just looking at s and p orbitals, then your space, you've got like a 4-dimensional space that's made up of, because there's 4 different ways that the field can wobble, kind of 4 dimensions along with the field can wobble. But your choice of how to describe the different directions is arbitrary, right? Because I can define a set of vectors, or like I can define a coordinate system where, I don't know, z is up and x is here and y is there and z is up. But I could also reach any point in this space in my room right now with a set of vectors that's pointing like this, where this is some combination of the previous x, y, and z, and so are these two. And it's arbitrary because the important thing is that there's 4 of them, and that they capture all the different possibilities correctly. They're orthogonal, right? Like if you had 2 pointing in the exact same direction, that's a problem because then there's a direction you can't get to with those vectors. But as long as you have things that are in a proper combination, so that combinations of them can get to any point, then you're fine. So these, when you see these hybridizations, these represent sort of different bases in these states, in these sets of states. So there's one where you divide it up in, here's the low energy state where there's no angular momentum. Here's the high energy state where there's no angular momentum. Here's the one where there's only momentum in the x direction. Here's the one where there's only, there's, I don't want to say no, but no net. Here's the one where there's more momentum in the x direction. Here's the one where there's more momentum in the y direction. These 4 states are independent, and we can add them up in different combinations to get different things. For example, if we add this one and this one, we'll get a state with some larger momentum in the x direction and in the y direction. And that corresponds to one that's going around in a circle, like I was saying before. But for the purposes of bonding, what atoms are trying to do is they're trying to keep the protons as far away from each other as possible, and keep their electron clouds as far away from each other as possible, because electrons don't like to be in each other's space. They start getting in each other's space, they physically can't, so they have to bunch up in weird ways, and bunching up causes you need energy to bunch up because you're localized in space, and which makes you delocalized in frequency space. So the way that for purposes of chemistry, the thing that is being maximized once you have these four things is different, and so you want to have a different basis, and the basis that you come up with is this sp3, where you combine all the previous four, and you get four that are identical to each other. They're just oriented differently, and there's a way to do that. They end up in like a tetrahedral structure, and this is as good of a basis to do all of the previous stuff as these ones. But what they don't have is nice properties in terms of like one of them has only momentum in a particular direction, and the other one only has momentum in a particular other direction and stuff. So for some purposes they're bad, but for nature it depends what you're optimizing for, right? So this is what nature optimizes for methane.
3CO, carbon, here's our touch, spread out 109.47 degrees.
This just happens to be the angles that you have in a tetrahedron. It's nothing really fancy.
Come on now, follow our lead. Come on now, follow our lead. Molecules take the shape they do, combining states of the quantum.
So there's another that one is, what is this, ethane? Is that ethane? Yeah.
Combining states of the quantum.
No, that's not ethane. That's a nitrogen. What is this? I can't remember the name of this molecule. It's something amine, methylamine. I don't know. Somebody tell me. But yeah, so this is still just like tetrahedral. That's that breakdown.
Quantum rules, like when a shell goes sp2 for sigma pi double bond.
Now so there's just a bunch of different ways that you can break down the states, right? So if you've got a molecule of this type that you're going to have two of the electrons bond over the top here, then you're going to have a different sort of constraint on the energy. So this can all be written down. This interaction can be written down in terms of like the s orbitals and p orbitals separately. It can be written down in terms of the sp3 tetrahedral orbitals if you want to, but like these are going to be some strange mixed combination of those, and it's going to be really confusing. Methanamine, okay. With a molecule that's double bonded, what you get is one set of electrons that are here. This is really expanded out. Really what's going on is you've got, like the way that you had those little balloons at the top and at the bottom, they just move in a little bit. So there's kind of like this sandwich of one electron pair here and one electron pair, just like sort of hugging it in an envelope over the top, like staying as close to each other as possible. But like these ones, there's not this big gap. Really what it is these ones the ones at the top and the bottom can't get in this one's space because of Pauli exclusion, right? So this is once again a cartoon, but this is mostly made of p orbitals. This is mostly made of s orbitals. So we call this one a sigma for s and a pi for p. And then these ones just hang around. These ones are free to go and connect to the hydrogens that they want to connect to. They kind of envelop them. So what you want is something that has a really tight like these two as tight as possible, and then these ones spread out as much as possible. And so you get these planar, like this planar three lobes here. Those are sp2 orbitals. And then you think of this as just like one p that didn't really do anything. So there we are. So there they are again. We're back to the old view. So here's our p orbitals. They're hugging real close. You've already now we're getting mixtures because the the orbitals that are first bonding these things together are all they're all here. There's all sigma bonds here, and this is really the tightest bond, the pair that's holding it together. Because electrons are filling up this disk, the other electrons have to. Methanamine isn't a thing. Okay, so what's it actually called? CH3NH2. Somebody, because I missed it in the stream before. I don't know. Yeah. So these these are pushed out by the electrons that already exist. Methylamine. Okay, I was right the first time. Dang. Isn't that what they use in Breaking Bad? So these ones are pushed out. They still want to bond because it's still energetically advantageous to them to get off of their little islands here and like spread out. So they end up like these sigma ones are really localized. They're stuck between two protons. But these ones, not only can they spread out between two of them, now all of a sudden they can spread out all over the place. So we get these nice resonance structures that are about to form.
They spread it in the molecule.
Yeah, so like this is another way of like the different ways that electrons can wave. Here's the lowest energy one. That's like a pair of electrons that are just waving. The only way that they're waving is up and down. There's a node here in between them. So they are waving up and down. They're avoiding these electrons here. But otherwise, they're just spread across the whole molecule, which is nice because the further around you're spread, the lower your energy can be because you're not contracted. Contracted waves are high in energy, remember. These ones have to be contracted a little more because now this pair has taken up the nice, the nice perfectly symmetrical version. So there's two things it can do. It can wave in a way that has one node, like still a node here and another node here. It gets kind of cross pattern, or it can wave kind of across the middle. Like this one's corner to corner and this one's side to side, I guess. So these are all waving kind of in complementary ways and like they're doing this really cool dance where they're like all avoiding each other perfectly to avoid the constraints of the fact that there's only one way. The field can only wave either 1 or 0. It's pretty cool, but it's just it's not like anyone planned it. It's just how it settles in. And then there's 3 other states that you'll see, which are the states that it doesn't pick because they're energetically sucky. And we represent all that complexity with just this nice little aromatic ring, because we just do layers and layers of reducing the complexity so that we can actually chunk our understanding. Yeah, here's the other possibilities of ways that an electron could wave across this molecule. And you'll notice that these ones have a lot more nodes in them. They're a lot higher energy. This one has a node here, 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 here. It's basically just p orbitals, but even more sort of stuck in their place, isolated. This one's a lot like this one, except that there's another node in between each one of the atoms. This one too, it's kind of like this one, but there's another node between these two atoms. So once again, more nodes equals more wavy high frequencies, which means higher energy, which means that generally you'll get knocked down from that into the lower ones and end up here. There's a cartoon of a triple bond. You would think of this as, the pair in the middle and then a pair hugging it here and a pair hugging it here. But we draw it out with these p orbital bonds up and down so we can see it. Because even this is immensely complicated. Someone's asking what are HUMO and LUMO? I have no idea what that means. So now we're gonna reduce. So we're gonna represent our sigma bonds as sticks again, and soon we're gonna reduce to another layer of complexity where we get rid of. I mean, we've already gotten rid of the protons and electrons in the middle here and just put C. I don't actually know those terms, HUMO and LUMO. We're gonna reduce to another level of complexity, build up a sugar. With me, baby, come bond with me, baby, come bond. Check out that chair configuration. If you take organic chemistry, you'll know that this is glucose, I guess. This carbon flips up and it changes from a chair configuration to a table configuration or whatever you want to call it. Boat, is that what they call it? Boat. It's been a long time since organic chemistry. Oh, LUMO is lowest unoccupied molecular orbital, and HOMO is highest occupied molecular orbital. Okay, that makes sense. So the lowest unoccupied would be those ones in the top rung, like above 0 but unfilled, and the highest occupied would be those ones that have one node but still are filled.
Come bond with me, baby, come bond. 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 Come bond with me, baby, come bond.
That shot wrecked my computer because it's just like to do this in After Effects is, you know, you start with like I start with this at least like so I combine all these things, and so this is like one of these is still like 10 or 15 lines, and I had all these like jostling. I think like I had all of them wiggling in a little way. No, these aren't wiggling yet. That's good. Didn't have them wiggling. I didn't do that until the next part. But even so, this is like 15 lines, and then so you take all this and you compose it into like a composition, and then you just duplicate it in After Effects, and you put them both in a new composition. You add it to the end, and then you like the way to do a fractal is just keep doing that, right? So I think I made this in one composition, this little fork, and then I was like, all right, well, I want to make glycogen. Glycogen's like a huge fractal tree of forks, so I'm gonna take this fork and like already this is like like 10 compositions laid on top of each other in one comp. And then I take this whole comp and I duplicate that and I make a bigger fork, and then I take that comp and I duplicate that and I put it in a bigger fork and like spread it out. And so by the end of it, I'm like 10 layers deep into After Effects, and there's thousands of little vector graphics things, and the computer just ground to a halt. It was a real challenge to figure out how to render this thing.
Come bond with me, baby, come bond. Come bond with me, baby, come bond. Come bond with me.
I don't really know why I did that. Like I'm kind of hearkening back to the previous structures that looked like that, but there's not really a connection between glycogen and the orbital or the aromatic ring. I just needed something in that place, and I thought it was kind of looked cool.
Come bond with me, baby, come bond.
This thing.
Come bond with me, baby, come bond. Polymers take the shape they do.
If you want to make your pro tip, if you want to make, well, first of all, if you want to make your molecules look a little more lively when you're animating, take all the little things and make them jiggle. Just give them a little bit of a wiggle function in After Effects. But also, if you want to do it in a way that doesn't kill your computer, which is not what I did here, because this section was really hard on the computer too, because it was doing all this Brownian motion stuff. What I figured out to do in Nanobot is that you can take one sort of like displacement filter and add like some sort of, I don't know, fractal noise to it, and then it'll make them all wiggle at once in a way that's a lot easier than adding wiggle expressions to every single little line and segment and stuff. But I didn't know that at the time, and unless you're deep into the weeds of animation and After Effects, you don't know what I'm talking about.
Combining base level residues like RNAs.
Yeah, I do like I do like how synced these are as well. Like it's a real, like with the bass, the boom boom pa boom boom pa, it like really punches in a nice way when these come in. Like my favorite one is when the proteins drop into the phospholipid bilayer. The boom boom, it's just really satisfying. RNase, ACGU. A residue is it's a unit of a chain of some kind of polypeptide. Polypeptide, like polymer. I don't know if residue is a general term for any sort of polymer, or if it's reserved for particular kinds of biomolecules. But anyways, it's just like a repeating unit. Base level residues. Here are the four bases: adenine, thymine, cytosine, and uracil. I don't know which one's which. ACGU. And fortunately, the way there is a way to arrange ACGU so that A bonds to, like, you can do it like, so I made one molecule and I flipped it in a mirror image, ACGU, and A bonds to U, G bonds to C bonds to G, G bonds to C, and U bonds to A. So I could get the lyric to actually line up with this nice sort of like stoplight animation thing, which took I don't know, is maybe is an inevitable consequence of combinatorics, but it took a while to figure out. Hey, hydrogen bonding. How does hydrogen bonding work? It's still a little unclear to me. Someone explain hydrogen bonding to me, and maybe I'll read it out. Oh, there's a weird little. So what happens with a peptide bond? So that's how proteins work with like these nitrogen backbone, carbon nitrogen backbone. And I got really lazy with the R groups because like there's a whole bunch of different kinds of amino acids. Each one of these is an amino acid being added to this chain. And the differences between different amino acids is they have these different groups, these different molecules basically on the ends of the sticks here. These R groups have like a whole bunch of different functions, and that's what makes them fold up in weird, interesting ways and attract to each other and all this. So there could be an aromatic ring here. There could be like an acid. There could be something with nitrogen or whatever, right? But I didn't want to do that much work, and it would have been super messy. So this is just R's here. But yeah, when these amino acids bond to each other, they actually do it by losing, like, one of the byproducts is a water molecule every time one attaches on, because they've got like one has an OH and the other has an H at the end. So they combine, they get rid of it, and they release a water molecule, and then you get this bond, peptide bond. And I actually bothered to animate little waters coming out of every time a bond was forming as these things were falling from the sky, which seems kind of excessive, but I was going crazy at this point. I was like, this is going to be the best thing ever. I'm going to take it to its limits. This I like traced. I managed to trace from some sort of animation and then make at least a cartoon of something that looks like a sensible protein. Let's see. Hydrogen bonding is basically magnetic attraction. The nitrogen steals the electron from the hydrogen, makes it a little bit positive, and the oxygen, on the other hand, just has a lot of electrons, and that's a little bit negative. Okay, I don't know if that's basically magnetic attraction, but that makes sense. Right. So if you've got an atom where the electrons are peeled away a little bit, and an atom where there's a little bit more electrons than usual, just from the way that electrons like to go into their lowest energy state, then one will be a little positive because there's less electron in it, and the other be a little negative because there's a little more electron, and then they'll want to bond together. So then you get these things between hydrogen H, which likes to be positive, and O, which likes to be negative. These little bonds that form, and you can solidify these structures. Cool. I mean, it's not magnetism because it's not. Well, yeah, I guess it is a dipole reaction interaction. I don't know. It's electrostatic. It's, if you're gonna say it's basically magnetism, it should have something to do with charges going around in circles. So another layer. This is the final layer of simplification. Well, I guess there's a couple more layers of simplification, but here's your nice phospholipid. I tried to give some curvy ones some cis bonds, because that's actually is what happens with your phospholipids. Sometimes there's these double bonds that cause them to crook, and that's really important for keeping your membranes from. There's a very delicate balance with these and with cholesterol and stuff that keeps your membranes just the right amount of like solid but liquid, kind of flowy at body temperature. So if you have too many of these, it'll be liquid and fall apart. If you have too many of these, it'll be too solidy. Membrane proteins sticking into them. All right, this also killed my computer to do, because you can imagine each one of these is built of a whole bunch of those little beta pleat sheets and alpha corkscrews, and then you put those in a big clump, and then you duplicate a bunch of those, and then you get a whole bunch of your phospholipids in a vesicle over here, and it's just it was not nice to the CPU. Let's put it that way. I decided to transition to the next level of simplicity before I got to the mitochondrion, because it's like there's no way I'm trying to animate a mitochondrion out of basic molecules. I have no idea what it looks like. I'm just gonna do that. So this ends up showing up in EvoDevo to start it off. And then this is a very unrealistic view of human cells. They don't actually have like little holes in between them, and they're all circular and forming this nice like grid, as if you put a bunch of pennies down on a table. But we'll get to the complexities of the different shapes that cells can have in the next video. So, something to look forward to. The chemical machine is best to do. The molecules take the shape of you. after this, I got really obsessed with that idea that you're a chemical machine, and it really came back. So it was kind of a through line through Evo Devo and then through the Nanobot song. But it's just cool to think like that's like the epiphany that I had one day when I was in physics class learning about these quantum fields. I don't know. There was kind of this moment of realization that I had when I learned that, like, this part that that electrons are also waves in fields, where like my mind sort of like one day coming out of quantum field theory class, my mind kind of tunneled up through all these levels all at once, and it was like I walked out and had this suddenly completely different understanding of the world, where it's like, holy crap, everything is these. It's like all the way, and I could see all the way up from this to molecules, to biomolecules, to cells, to me, to the buildings around me and everything. Like, wait a second, I feel like I just discovered what the world is and what I am in some way. And that was something that I always really wanted to find a way to share. And I'm still trying to tackle that at different angles. I think like my new quantum field theory video that's going to come out is also doing that same thing, like showing that more directly, kind of skipping all these intermediate steps. But it's just one of those things. I'm like, people need to know about that. That's cool. So yeah, and then he walks off, and that's it. I'm gonna skip the ending on this one because it's just an ad. It's an ad for this this app that I did, and we don't need to watch the ad. So thank you for sticking around. It's 5:20. We went a little bit overtime on this one, but that's okay. I'm allowed. It's my stream. It looks like 87 of you decided that you would also be happy to stick it out. So thanks for doing that. We're gonna go back to we're running overtime. Should we do daily discussion?